My name is Chris Durrell, and I'll be taking you through this presentation on FLAIR campaigns, which are complete radiometric spatial calibration events for your satellite or constellation. First, an underpinning of the technology that comprises the FLAIR systems. The specular array radiometric calibration technique, or SPARC technique, is a method that uses convex curved mirrors to relay the sun to the satellite using the sun as a calibration source. This innovative technology provides an engineered known point source on the ground of known spatial dimension, and also in coupling with a solar radiometer, which provides measurement of the sun's radiance, and the atmospheric extraction provides a radiometric and spatial data package to the orbiting or airborne platform that can be used to provide a complete calibration event for that satellite. We can either use single mirrors or we can use arrays of mirrors to relay more signal, or we can use clusters of point sources to provide specific spatial information. There's a citation at the bottom of the slide providing more information if you're interested in discovering the specular array radiometric calibration, or SPARC technique. This diagram shows how the SPARC system is actually activated and works during an overpass. So the first set of information is the user puts in their information about their satellite into our web portal. That information is relayed to our system, which the computer system resides on a radiometric tower, and then the system mirror turret activation is controlled through the radiometer exercise. The radiometer opens, measures the solar radiation calibration, which then in turn is used to measure both the upwelling and the downwelling atmospheric transmission. And then the mirror system is opened, targets the bisection of the angle between the sun and the satellite, and uses the mirrors to relay a fractional amount of energy from the sun to the satellite, thereby providing a known point source to the overpass instrument. This can be used with satellites, airborne, or UAV technology. The FLAIR network is a series of distributed, automatic, tracking SPARC mirror sites for satellite calibration or airborne calibration and validation in both the radiometric and the spatial domains. You can access the network and schedule calibration events with these sites remotely. You don't have to be at the site. The calibration and validation is handled by LabSphere and through the automatic system. All of the capabilities of the FLAIR are available on these nodes. You don't have to schedule campaigns or physical events. These can be scheduled easily and frequently on demand, and the results for a calibration event can be built either through a single collection or built over time as a result of multiple looks. However, if you're looking for rapid results across multiple satellites or multiple ground sample distances or different radiance levels in the same scene, we can provide data-rich events and we can handle complex situations for diagnostics, and that is really more of a targeted FLAIR campaign event. So what is a FLAIR campaign? This is a field event where LabSphere personnel head to the field in the classic way that has always been done for the satellite and remote sensing community, which is we take Lambertian targets and field radiometers, spectral radiometers, out to a specific site for a measurement event and an overpass event of an airborne or a satellite sensor. However, we're now leveraging this new SPARC technology to produce multiple point sources in a single event, and those can be tuned to one or more sensors. Campaigns are excellent options for cross-calibrating multiple satellites, simultaneous native overpass, or even different types of sensors, say like a UAV platform and a satellite, or an airborne and UAV platform, and also looking at different spatial information. Determining linearity or absolute gain coefficients can be also determined in these campaigns. Providing an oversampled point response function, MTF, or other type of spatial analysis, or commissioning new satellites while they're just scudding up and they're diagnosing their performance, or if you're having problems with your satellite, then these can be very helpful in rapidly diagnosing current issues. Flare campaigns are customized for your sensor and require interaction with your design team and our design team. They're NIST traceable, and they use the automated sites while also using some static mirror points that we set up specifically for the events. And that increases the data generation and provides a lot of very important sensor metrics, all under the same conditions and the same solar radiance measurement provided by the radiometric tower. So to provide a little bit more visual aspect of what that looks like, so what we have laid out here is some pictures from prior campaigns showing different types of mirror arrays and also what those look like from satellite imagery. And then also what the layout of a typical array might be, where we have automated turrets in the radiometer, as well as manual arrays, and perhaps even Lambertian targets laid out to provide some radiometric baselining or perhaps some BRDF capability, which I'll talk about in a bit. So again, a bit more of a blow up here on what a nadir look campaign might look like. So here we see several arrays laid out. Again, this is just the same picture from the last slide, but blown up. We have radiometric manual arrays. These are these down here in addition to the automated stations. These are multispectral band optimized for different types of Lambertian equivalent or LE signal levels. And then we have spatial arrays, which are specifically set at specific distances or specific sizing for different types of band targeting, pan and multispectral, or different sensors going over at the same time with different GSDs. So that's what a campaign is. Let's take a look now at what kind of spatial performance you can get from these events. First, a bit of an homage to the existing methodologies that are out there. The way that spatial quality assessment is done typically is using edges or lines. Edges may be naturally occurring, such as coastlines or buildings, or specific geographic areas. Lines also bridges or runways, other types of naturally occurring events. These are used classically for this type of assessment, but you have to build a lot of those images and survey a lot of those images because they're not perfect lines and they don't provide really clean information. So what we want to talk about here is the point method, which is what we're introducing to the new toolkit. So the edges and lines are great and will continue to be used, but the point methodology also provides a lot of advantages, including omnidirectional sampling and also the ability to provide a true impulse response. So let's get into that. This shows some results using some work that Lapser has done over the last couple of years with edges and points and lines. And you can see that you get similar results for all three of those methodologies. The advantages of the points is that they're omnidirectional, so we get along and cross-track information without having to align the edge or the line to either the along or the cross-track direction. So the point sources provide a single overpass capability that the edges and lines don't. However, to develop a truly rich data set for the point sources, you probably do need to have multiple point sources in line to catch for phasing and get a truly oversampled point spread function and provide the result that you see here. So typically laying out multiple sources or looking at the same point source in a series of single overpasses is required to develop a low uncertainty point spread function or point response function from the mirror sources. The point sources also can be used to process the imagery at any level. So aside from the point response function, you can also derive MTF and other types of algorithmic kernels from different levels of imagery taken with the same point field. We can provide ground control points as well. We know where those point sources are, usually to less than 2 centimeters, and we can provide that information to you as well. That helps with geolocation and geopinning of the imagery. And then we can also provide, if we lay out specific types of point pairs or other types of array geometries, we can provide insights and forensics on the imager itself, all the way back to the Zernike kernels of the optics. Another truly unique thing that you get from the point sources that you don't get from classic Lambertian targets is that it really helps to diagnose focusing, smear, and band misregistration issues. And this is really hard to detect with a large area Lambertian classic type technology. Here we can see that we have some point sources in scene. These are supposed to be well-contained point sources. You can see that we get some blurring and some spread here. So in this one we see an along and a cross-track dependency that again pops right out in a single image. Here we see some defocusing that the user was able to take both of these images and correct the sensor. And then here we see some band misregistration issues. You can see here the independent bands can be pulled out from the single point source, and you can use that to diagnose exactly what's going on with the sensor in the blue, green, red, or near infrared bands. So that was the spatial side. Now let's talk about the radiometric performance results that you get from FLAIR campaigns. The radiometric performance of the FLAIR system is our radiometric tower, which includes both a Vernier spectrometer and SWIR bands. So here we see the spectrometer band, which covers 350 to 1000 nanometers with a 1 nanometer resolution that provides incredible detailed information about the atmospheric transmission and the solar radiance. And then we also have a banded 8-channel near SWIR radiometer that provides pinning in 8 channels to the continued atmospheric information from 900 to 2500 nanometers. So the radiometer does the measurement of the sun and measures the downwelling transmittance of the atmosphere. Then we use Modtran to pin that downwelling measurement to an upwelling atmospheric model. This FLAIR radiometry can produce atmospheric insights as well as the radiometric data that we're interested for the satellite performance. And the inversion algorithm is suitable for atmospheric radiative transfer modeling. So after the solar measurement is complete and the atmospheric transmission is removed from the signal, what we're left with is the raw radiometric response of the sensor to the FLAIR signal. That, combined with the relative spectral response given to us by the customer, the RSR, for each band, allows us to deliver a radiometric performance coefficient for each sensor, both expected and the actual measured. That is a traceable measurement. Our traceability for the FLAIR system right now is about 3.5%, 1 sigma. One of the innovative parts of the FLAIR targets is, though, we can lay out multiple targets that provide multiple signal levels. Here we actually see in scene some of the FLAIR targets, just to provide some reference. This is in the field of regard of the sensor, and this is after the sensor has passed out of the field of regard. The mirrors are still there, but they're no longer visible because the sun is not being relayed into the field of regard of the sensor. What we have in this multiple array image, though, is all of these different array levels that we can be provided. And since these are uniform aluminum mirrors, they basically provide a spectrally independent linearity assessment of the sensor performance. Here we see a blow up on the extraction of that image, and we can see that we have different signals here with different numbers of mirrors in them. They all look like point sources. They're all sub-pixel. However, they're relaying different amounts of signal back to the sensor. Those different amounts of signal create an empirical line method. We call this the mirror empirical line method, or the MELM, and you can see that every single band now has a relative linear response prediction from the different levels of signal. In addition to the MELM, you also can provide low reflectance verification, because each of these lines passes directly through zero, which is a very hard thing to do with Lambertian targets. We can provide absolute gain response of the sensors, do a linearity assessment, and signal to noise assessment of the sensor response. So FLAIR also gives you this band insight almost automatically when you start to look at these images. So here we see a multispectral image. We've blown that up. Right away, the analyst can see that there are band differences in this point source. It should all look like a white dot, but it doesn't. And this is what is the band misregistration popping out. So immediately visually you see that. That can also be quantified and automated to extract the point response function, and then you get it quantitatively here, and that can really help you to diagnose what's going on with, say, some of your color or radiometric information. This provides both a long and cross track, and it is truly a powerful aspect of the FLAIR information. So I want to also talk about BRDF, which is a unique capability of the FLAIR system. Now this is a bit more of a complicated exercise, because now we have to employ both the tracking aspect of the FLAIR mirror system and the customer's ability to point at various angles at the FLAIR system. So here on the left, what we see is the satellite executing a series of images at different angles as it's flying over. So think of it as pivoting about the FLAIR image and using that as a source of constant point source radiance. And these are the angles here that the satellite was capturing. That information then can be translated to direct reflectance information. And immediately what you see here, the blue line is the ground truth, but what we see with the angular overpass is there's some angular dependency of this native ground target here, this grass target. Not so much in the visible, but certainly in the near infrared, we start to see that really jump out. The reason why we can extract this is because the FLAIR system is tracking the satellite through this angular overpass, acting as a constant point source. So anything observed in the scene by the satellite taken through those series of angular overpass images can have a radiometric extraction done on that. And if there's a radiometric variance due to BRDF or angular reflectance, then that jumps right out in the signal. So this is a unique and very powerful technique that FLAIR can provide to pointing and tasking satellites. So I'd like to sum up some of the benefits that we've talked about so far. There are fundamental outcomes from a FLAIR campaign that are delivered as part of the event. First, complete radiometric and spatial performance assessment. We can serve multiple satellites or constellations. We use both the static and fully automated synthetic targets in that effort. These campaigns can be targeted at 0.3 meter to 5 meter GSDs. We deliver the point response function, band radiometry and registration information, geospatial control points. This applies to any level of imagery that you want it to. And then we are a traceable absolute response function. In addition, if you want to contract advanced services such as BRDF ground truth or the mirror empirical line methods, and the extraction of signal to noise ratio gain or dark target verification, we can do that, or we can also provide atmospheric data as part of the extraction package. That's the end of the presentation on flare campaigns. This has been a brief overview. If you have any questions, please feel free to reach out to any one of us here at the bottom of the screen. We'll be happy to answer those questions. If this has gotten you interested in what flare campaigns can do for your sensors, this is a limited time opportunity. We're running the campaigns this summer, and there are limited spaces available for these campaigns. So please give us a call to sign up for your flare campaign today, and we'll be happy to work with your team to develop a statement of work to provide diagnostic information using the flare system for your sensors. Thank you.